Hello everyone, I'm Deevashwer. I have been involved in the development of the PyBV and PyYASHE repositories of the OpenMined project, and I'll be demonstrating the same today. I'll be going through the functionality that each API currently provides, so let's get right in. In case someone has a doubt, PyRegion is a class that we created so that Python can interface with the PyRegion variable, which is an abstraction of all the mathematical structures Py supports. In both the APIs, the plain text is first converted to polynomial. For example, we are encrypting a list of integers, say 1, 2, 3. It will be first converted to a polynomial 1 plus 2x plus 3x squared and then will be encrypted. So let's get to PyBV first. Um, these numbers are actually the parameters for the scheme. 2048 is the maximum degree of the polynomial that we'll be dealing with, and it is also the maximum number of messages that we can encrypt in a single ciphertext. 61 is the bit size of the modulus that will bound each coefficient of the polynomial, be it a ciphertext or a plain text. 2030 is our plain text space, so all the messages that we'll be encrypting will be less than 2030 in magnitude. 8 is the standard deviation for the error distributions from which we'll be deriving our secret keys and the errors associated with each ciphertext. Yeah. So we are so to start with, we are encrypting 3 ciphertexts. No, we are encrypting 3 plain texts. The first one is encrypting 4. The second one is encrypting the list of integers 2, 4, 8, 15. And the third one is encrypting another list of integers. So the demo will follow this pattern. A statement will pop up displaying the statement to be executed next, and we'll move sequentially through these statements while observing the outputs. So these are the 3 ciphertexts that we produced. So for the first part of the demonstration, we are doing a ciphertext multiplication. This is the exact syntax that we are following to do it. I've used CT4 to represent the ciphertext because I'll be using it later. Okay. So this is the decryption output. It is exactly what we expected. The next part demonstrates multiplying ciphertexts that have encrypted 2 lists of integers. So let's see what it. Yeah. So as you can see, the size of this the decrypted ciphertext is greater than the size of the plain text that were encrypted in the first place. This is because we are actually multiplying. When we multiply the ciphertext, we are actually multiplying the 2 polynomials that were encrypted within them. So the degree of the decrypted ciphertext will be equal to the sum of the degrees of the inputs, plain input ciphertext, and minus 1. Okay. Next, we demonstrate plain text ciphertext multiplication. This is the syntax that we use to do it. Pretty simple, similar to how you multiply 2 integers. Next part is the homomorphic addition. Okay. How I can tell that all of these are decrypting correctly due to these zeros that are appended after the actual decryption result. These would have been garbage had the decryption failed. So yeah. This is an example of nested nested operations. We are the current implementation only supports one homomorphic multiplication, so that's what I've done here. I'm adding multiple times, but actually there's one homomorphic multiplication going on. To overcome this problem, we use a technique called bootstrapping. We are currently working on it. So to develop the BV tensor, uh, interface, we are using a decryption oracle as a replacement. Yeah. So now let me show you the actual decryption output, what I actually get when I decrypt a ciphertext. Yeah. A list of 2048 integers. Because, as I told you, we can encrypt maximum 2048 integers in a single ciphertext. This is how you decrypt a ciphertext. Cd.decrypt, it's that simple. I'm only outputting the first 20 integers because of the lack of space. This is the actual decryption output. Now let's see the error terms associated with each ciphertext. For both the demos, I've only outputted a single error term because all of them will be similar. I've just outputted one because it will be hard to see the difference if I output all of them. So let's see the error term for CT1. This is the error term, which is definitely smaller than the modulus Q. Yeah. When I did CT1 times CT2, when I did CT1 times CT2, you can see that the error term actually got double in, not got exponentiated. Yeah, it doubled in bit size. Now let's see for ciphertext. Yeah, there's an error here. Actually, I'm multiplying CT4 with CT4, and CT4 was actually CT1 times CT2. So basically, I'm doing CT1 times CT2 times CT1 times CT2. Yeah. So it was expected that the error will actually double in bit size, but it does not seem so. Let's print the modulus. Yeah. So it happened because it actually doubled in bit size, but since our modulus was less than that, so it wrapped around the modulus and we get this value. And as I told you, we decrypt correctly only when the errors do not wrap around the modulus. So this shows that the current implementation for the current parameters only supports one homomorphic multiplication. Let's see what the actual ciphertext looks like. It's a polynomial of degree 2047, and each coefficient is bounded by q, our modulus q, and that is exactly what I said. So that's it for the beefy demo. Let's get to the PyYASHE demo. So these are the parameters for the PyYASHE. 3329 is similar to 2048 and PyBV, the maximum number of integers that we can encrypt in a single ciphertext, and also the maximum degree of the polynomials that we'll be dealing with. 128 is the bit size of the modulus. 256 is our plain text space. Yeah. Now this is another additional parameter that PyYASHE uses, or YASHE uses. If you increase this parameter, it leads to more efficient implementations, but it in turn leads to less multiplicative depth. So it's a trade-off between multiplicative depths and your speed, the speed of your implementation. And instead of using one parameter for the error distribution, it uses two, one for the secret key and another one for the errors associated with each ciphertext. Now this demo follows a similar pattern. We are encrypting 3 ciphertexts. Also, this is a leveled implementation, a level homomorphic scheme. So to tell what is the difference between a somewhat homomorphic scheme and a level homomorphic scheme, consider that the modulus size is x raised to power 16, and the magnitude of error in each fresh ciphertext is x. So when you multiply 2 ciphertexts, the error grows as x squared, x raised to power 4, x raised to power 8, x raised to power 16. So you only get a multiplicative depth of 4. But with a leveled homomorphic scheme, the error increases by a linear factor. So assuming that it increases by x. So if we start with a fresh ciphertext with an error x, it will grow as x, x squared, x cubed, x raised to power 4, x raised to power 5, and so on, giving us total of 16 multiplication. So that is a lot compared to the somewhat homomorphic implementation, and basically it exponentiated the multiplicative depth. So let's get to the demo. So for the first part, we are doing a ciphertext multiplication. This will be a bit slower because I've set the parameters too high. Now CD2 times CD3, just as we expected. Addition, homomorphic addition, simple. Now since I've set the parameters so that it at most allows 5 homomorphic multiplications, so this will work for the PyYASHE. It will take a while, and yes, we get the right output. Let's see the actual decryption output. It is similar to the PyBV one, just that these will be 3329 integers, because I set n to 3329. The error term associated with fresh cipher. Now we'll see how the error terms change. Now this is the magnitude of the error in the fresh ciphertext. Let's do CD1 times CD2. Yeah, it actually did increase by a linear factor, but you are unable to see it because the linear factor is approximately equal to the magnitude of the error itself. So let's multiply it again. So yeah, this is not correct. Here also we are actually doing CD4 times CD4, and CD4 was actually CD1 times CD2. So we are again doing CD1 times CD2 times CD1 times CD2. And you can see that the error actually increased by a linear factor. Had it been the PyBV implementation, the bit size would have doubled. So this is level homomorphic scheme in action. Let's see the modular size. See, this is greater than the error in our second stage ciphertext. That's why it decrypts correctly. What was the actual ciphertext? Again, a polynomial similar to what we had in our PyBV scheme. So that's it for the demo. In case you have any doubts, you can contact me on Slack. My Slack ID is Deevashwer. Thanks for watching.